Good afternoon, sir. We are Group 3. So today I want to introduce our final project, Enhancing EV Charging Optimization with Deep Reinforcement Learning in SustainGym Environment. And here's our group members, Xiao Shun Hong, Jayu, me, and Omar. So I'm going to talk about import libraries and data preparation. And here's our import libraries. Second, the dataset preparation. The init methods initialize the data generator by setting up default values and loading the dataset. It sets the EV charging site as Caltech and defines attributes such as requested energy cap. The maximum energy requested is set to 50 kilowatt per hour. The simulation day set to 2023, December 26. And the time step duration, each time step is set to 5 minutes. The CFX file is read into a pandas data frame with the data limited to the first 100 rows to ensure efficient processing during development or testing. Now, this is the dataset methods provide a way to ensure reproducibility by setting a fixed random state. This is done using a NumPy library and helps guarantee that any operations involving randomness, for example, random EV attributes, produce consistent results across different runs. And here is the event queue. The get event queue method generates a simulated queue of EV charging events along with a list of EV objects. It initializes an empty event queue and calculates the number of charging stations, such as num+, based on the column in the dataset excluding the time step. For each row in the dataset, it loops through all charging stations, creating a battery object for each station with a capacity of 50 kilowatts per hour, a maximum charging rate of 7.2 kilowatts, and an initial charging of 10 kilowatts per hour. The corresponding to each battery, it creates an EV object with attributes such as an unique section ID, arrival and departure times, a requested energy of 20 kilowatts per hour, and the station ID. Each EV is associated with an event defined by its time step, and these events are added to the event queue. The method finally returns the event queue, the list of EV objects, and the total number of charging stations. The get more method extract more is a marginal operating emissions rate value from the dataset. It assumes that all columns except the first time step contains more data for different charging stations. The method skips the timestamp column and returns the remaining data as a NumPy array, which can then be used for emission calculations or other analysis in the simulation. Once initialized, the instance can be used to generate EV charging events or more data. The get event queue method creates a queue of EV charging events and corresponding EV objects, while get more provides more data and further processing. These outputs can be integrated into simulations to model EV charging operation and emissions accurately. Now I will pass it to Shu Hong to continue.
Good day, sir. My name is Xiao Hong, AIT306. Today, I'm going to talk about the environment initialization for our final project, which is for the action projection and also step function. So, for the action projection, we got the input variable action demands and max actions. So, the process will be like click the proposed action to ensure they are both in allowable rates and station demands. The station means the charge EV station, and the output will be the feasible charging rate for each station. And the function and variable we refer to the EV environment from the SustainGym. And also the step functions. We got an update time step, increment the simulation time by 1 step, and also the code will be generating for the charging schedule will be cover the normalization in the AMPS and also make the charging rate to the specific station in the environment. And then we start with the environment simulation. Later on will be like linked to the deep reinforcement learning, which is deep Q network. For that part, I'll pass to my teammates. But now I'm talking about the simulation. The simulation will simulate the charging, apply the schedule and following time, and also will be like gathering the feedback. And the parameters will be observation, rewards, and also the info retrieve the details of my current state. Next, I'll pass to my teammates to talk about the deep Q network.
Hello, sir. My name is Liang Jiayu. I will introduce the DeepQ network agent implementations. The DeepQ network agent learn decision-making strategies by approximating the Q functions, which evaluates the value of taking a specified action in a given state. The Q function combines the immediate reward from an action with the future value of the optimal next actions. Discount by a factor gamma to balance short-term and long-term rewards. The agent initializes with size, state size, and action size to define the problem's dimensions. It uses a memory buff to store up to 2000 past experience for replies, which help reduce data correlation and enhances learning. The experimentation rate epsilon manage the trade-off between exploration and exploitation, gradually decaying toward to minimize value using epsilon decay. The learning rate control the speed of model update. The agent also built a neural network to predict Q value, guiding the decision making. And the neural network flow sequential architectures. The input layer consists of a dense layer with 64 neural and ReLU activation, accepting input with dimension equal to state size. A second hidden layer with 64 neural and ReLU actions capture complexity feature, and the output layer has action size neural with linear activation, generating Q value for each possible actions. The model is compiled to use the add-on optimizer with the specified learning rate and the mean square error as the loss functions. The active method selects actions based on the exploration or exploitations. If a random number is less or equal to epsilon, a random action is chosen. Otherwise, the action with the highest predicted Q value is selected. The reply method train the model use a batch of the expression from memories. For each expression, a target Q value is computed. If the episode is not done, it is include the discount future Q values. Otherwise, it is just the immediate reward. The models weight are updated and the epsilon decayed to shift from the exploitation to exploitation over time. That's all my part. Thank you for your listening.
Thank you very much, Yayu. Good morning, everybody. My name is Omar, and I'll be taking care of presenting results and discussion and conclusion for you. So let's get right into it. So yeah, after we finish training our agent, this is the graph that we obtained. Now this graph has total rewards graphed against episodes, and there's many things we can actually learn from this graph, right? First of all, we can see that the agent was trained over 100 episodes or 100 epochs, and the agent does seem to be discovering new policies throughout training. As you can see, there's lots of fluctuations, spikes of reward, which shows that the agent has discovered a new policy that it's learning, right? And specifically at episode 64 and 80, where you're going to have the biggest spikes in the graph. But the negatives of this is that there's somewhat inconsistent reward improvements. Overall, in the graph, the reward spikes should gradually get bigger and bigger and bigger and bigger, but the flow overall of the graph seems to be somewhat inconsistent. This could be due to the complexity of the environment, and some hyperparameter tuning needs to be done to the event, right? For the conclusion, so we prepared the Power Grid dataset, we tweaked the environment to our needs, and we trained the agent. And the agent did show some positive signs of learning. And our study shows that you can, in fact, use reinforcement learning agents to optimize EV charging mechanisms and save energy. Now, what are some of the limitations that we face? First of all, we've got scalability. Well, since this model struggled with a complex environment that came from a data set, which was around 9,500 entries, it will definitely struggle with the real-time applications where you're going to have a lot more entries. And secondly, computational power is a limitation as well. Since we're learning on college computers and training this model on a laptop, it struggled a lot with performance, and it didn't give us room to try and optimize hyperparameters or numbers of episodes, as it would take very, very long time to train on our PCs. So, what are some of the future work we can do? We can try using different algorithms or improve our current algorithms. We analyze soft actor critic in our previous assignment. We can probably implement it here and see if we obtain better results. Secondly, we need to refine the reward function. Some, as if you could see from the graph, some parts would be flat. If we would to implement high rewards, low rewards, a more variety of rewards overall, then the graph might appear smoother at the end of the training, right? So yeah, that's it. This is your place to shine. If you have any questions, feel free to ask, and thank you very much.